Okay, guys. A couple of things I want to go over today. I want to review mean value theorem for 3.2. I want to review Rolle's theorem for 3.2. I also want to do some review of first derivative test, which is just creating the first derivative sine line, finding critical points, determining intervals of increase, decrease, intervals of locations where there's a relative max, relative min. Okay. And then we'll move into 3.4 today, which is talking about test for concavity, which is the second derivative sine line and creating information or identifying information about the curvature of the graph and the intervals of curvature. So if you guys turn to page 4, and I want us to just review, go through a set of review here, just to kind of give you some idea what's coming up here. So we'll do 3.2, 3.3 review, followed by 3.4. If we don't finish 3.4 today, we can finish that tomorrow. But tomorrow, I'll give you guys a quiz review packet, which we can work on Friday. And then we can also work on Monday, and then the quiz will be Tuesday. I'll be holding help sessions Monday and Tuesday, going over the parts of the review that I don't have time to go over in class. But when I give you the review packet, it will have all the solutions on it. So encourage you to begin working through that review packet in preparation for Tuesday's quiz. Okay. So page 4, mean value theorem. So here's the big idea with mean value theorem. The big idea is that we want to find a guaranteed slope. Okay, so part B says we're just going to look at part B. Use mean value theorem to determine the point on the interval from -1 to 2, such that the tangent line is parallel to the secant line. So all that's saying is we want to know where along the graph is there a slope that is experienced between these two endpoints. Okay. So at the very least, they're going to give you the intervals to work with. And this problem is nice because it already gave you the order pairs. What if it didn't give you the order pair? What would we need to do with these x values? Good. That plugs into the original equation and get those order pairs. So the first thing that we want to do is we want to take those points. Sorry, -1, 4, and 2, 1. And we want to gather the slope that we're targeting. Okay. And you're always going to do this with mean value theorem. You're always going to try to figure out what is my goal, right? And the goal is always what is the slope between the endpoints. So let's first find that slope. Change in y over change in x. And what's that slope? Three over -3, which is the same thing as what? -1, okay. So this is the target slope that we want the derivative to help us find. Okay. And if you look at the graph here, this is, you can visually see, that makes sense, right? Slope of -1 here. And the derivative is going to help us figure out where along this curve is there also a steepness of -1 at an exact point. You can kind of imagine that it's going to probably be somewhere around here. Or you can kind of imagine a slope that's parallel to that slope of -1. So now we're going to jump into the mean value theorem. The first thing we want to establish is if we want to do mean value theorem, we want to go through our conditions. All right, so our conditions is that our function is continuous on the closed bracket from -1 to 2. Establish the function is differentiable, smooth curve, parentheses though. And now, mean value theorem, we're just going to set the derivative equal to the slope that we're trying to target. So what's f prime? -2x. So we're going to ask the derivative, when is the graph going to have a slope of -1? So we're always going to take whatever target slope we find into the derivative variable and solve for x. Okay, we want to make sure that we never want to insert the slope into the x, right? Because that's a mismatch. You want to put the slope into the correct location. Solve for x, and what do we get? Divide by -2, x equals 1/2. That makes sense, right? You look at the graph here, it looks like it's around 1/2 when the graph looks like it's reaching about that slope of -1 that we are expecting between the two endpoints. Now, the final thing is, it says, use the mean value theorem to determine a point. So a point requires both the x and y value. So I know that my x value is 1/2. So how can I find that y value at that location? Plug back into the original, yeah, because I want to find a physical location, yeah. Okay. Any questions with mean value theorem? So you're always just trying to figure out what is the slope between the endpoints, and once you arrive at that slope, you find the derivative and you just set the derivative equal to that target slope and you solve for x. That's all there is to mean value theorem, but it does require us to write out our conditions and to understand the steps that's involved. Okay, so in a very similar way, we also have Rolle's theorem, and Rolle's theorem is just kind of like a subset of mean value theorem. So if you guys can turn to page 7, and let me just do a Rolle's theorem. I don't know what's that. So Rolle's theorem is very similar to mean value theorem. It's just that when you find your endpoints should be directly horizontal from each other. Meaning that with Rolle's theorem, we want the 2 points to be directly across from each other, because the slope that we want to guarantee is not just any slope. It's a slope of 0. We're trying to find a location where there's a slope 0. And we can only guarantee that if the endpoints produce the same y value, which will allow for us to draw a horizontal line between them. But the first things will still apply. We're still going to establish that our function is continuous and differentiable. So we'll write down those conditions. Nice thing is when you deal with a polynomial, this is automatic. You don't have to even worry about any issues with your conditions. I'm looking for these statements on your quiz and your test as well, writing out these conditions. Okay, so the third thing is we want to find the order pairs, just like how we did with mean value theorem. But mean value theorem, the order pairs don't have to be a certain way. With Rolle's theorem, it does. The x to y values have to be the same y value. Okay, so let's see what happens. We'll find f of 2. And we'll find f of 6. Okay, so 4 minus 16 is negative 12 plus 5, negative 7. (36 minus 48 is negative 12 plus 5 is also negative 7. So is this going to fulfill the condition for Rolle's theorem? Yes, because these y values are the same, which means that if you were to graph it, they're going to be directly across from each other, which means that the slope is always going to be what? 0. Good. And that's what we do. We always set the derivative equal to 0 for Rolle's theorem because our points should be directly across from each other. If these are not across from each other, if they're different y values, then it'll fail Rolle's theorem, but it could still apply for mean value theorem. It just won't apply for Rolle's theorem. Okay, so just like with mean value theorem, we're going to find the derivative and set the derivative equal to the target slope. So what's our derivative? Now you're going to take that target slope, insert it into the correct spot, into the f prime location. Make sure that you don't put that 0 in for the x, right? We already know what slope we were after, but we're after the location. And that's what the derivative is going to tell us. We're going to give it a slope. In return, it's going to tell us where that slope is going to occur. X equals what? 4. That's our C value. Our C value is 4. And if we double check, our C value should always live between the endpoints, and it does. If it doesn't, something went wrong. If we came this far, we should be guaranteed a location, right? We shouldn't be left with no solution here. We should always be left with something that we can provide as an answer. So that means on this graph, when x equals 4, the graph is going to experience a slope of 0. So I just want to do a quick run through of mean value theorem and Rolle's theorem before we do a full review tomorrow. Any questions so far? All right, I want to do a couple review problems with first derivative test, and then we'll look at test per concavity. So if you guys can turn to page 11, and let's do 21, and we'll do 33. So first derivative test, it should feel very familiar because you've done this with particle motion, right? Particle motion, you found your velocity, you set your velocity equal to 0, you found your, you create your velocity sign line, you tested each interval, and then you did interval right, interval left, depending on whether you have positive or negative. So the same process, it's just that now we're calling it f prime instead of velocity. And then we're calling critical points instead of velocity 0. And then instead of moving right, moving left, positive and now is not going to mean increasing, and negative is now going to mean that the graph is falling. But it should feel very familiar. You know, we've done the quiz with particle motion, so really now we're just calling it the first derivative test. Okay, so first things first, we're going to find f prime. Go through power rule. set the derivative equal to what? 0, right? Just like how if we're doing velocity. Now, if there was a numerator and denominator for your derivative, you have to set both the top and the bottom equal to 0 separately. Okay, so we can take out a GCF of what? 6. Continue factoring. Solve for x equals -2 and 1. Now you're going to place those critical points onto your slope sine line. Okay, choose values in each slope interval. So I can choose -3, I can choose 0, and I can choose 2. Okay, where do we put these test values into? Yeah, factored form of your derivative. Quickest way to get the sign that you want to look for. We can ignore the 6, that's a positive value, so it has no impact on the sign. So just -3 for x, that's negative. -3 and for x, so negative times negative is positive. So I'll put a positive. And I like to use arrows to indicate how the graph is moving. So in this interval, the graph is going to be rising. So it kind of gives me a picture as to how the graph is moving in that interval. Okay, next up. 0 for x. Positive times negative is negative. So the graph is going to be falling. That's 2. 2 for x is positive. 2 minus 1 is also positive. Now, as soon as you populate the sign and the arrows, go ahead and make sure that you cross out those test numbers. I still see some of us wanting to involve those test values, but you're not going to involve them anymore. The only purpose is to fill out the signs. After that, you're only relying on infinity, -2, and 1 for all your statements. Now, we can have an idea how the graph is going to look, right? The graph's going to rise, fall, and rise again. So the graph is going to have this shape. We may not know exactly where these ordered pairs are, because we'll have to look at the original function, but at least just by the slope sine line, we have an idea how the graph is moving. So what do you expect at -2? What's special about this point here? Relative maximum, okay? And then what about at 1? Relative minimum, okay? And then you would say interval of increase would be where? Yep, and then 1 to infinity. Interval of decrease would be from -2 to 1. Good. So let's practice writing out those 4 statements. If I want to find the relative max, I know the x value is at -2. How would I go about finding the full order pair? Back into the original, right? So I just want to make sure that we kind of have an idea when to use the derivative, when to use the original function, right? The derivative is going to help you fill out your sine line. But then once you locate the physical place for your max and min, then they go back into the original function to find their y values. Okay. So as you write out your statement, on the quiz, I'm also looking for these very specific because statements. Okay. So let's practice writing them out. You're going to say increasing from -3 to -2. You can say union or comma. You don't have to use that notation if you don't want to use comma. to say that you want to skip to the next interval. But I'm looking for these statements. Because f prime is greater than 0. Decreasing because f prime is less than 0. Relative max because f prime changes from positive to negative. Relative min because f prime changes from negative to positive. I'll be looking for those because statements on your quiz, so let's practice writing them out. Also, on the AP exam, if it's a free response question and they're asking for justification with the slope sign line, that's what they're looking for. They're looking for these because statements in very specific ways.
Can you explain the relative max?
Sure. So relative max is this point here. And we can guarantee that's a relative max because the slope, or f prime, is going to change from a positive slope to a negative slope. So at that interchange, when it changes from positive slope to negative slope, is where that relative max occurs. And then relative min is occurring at 1 because the slope, or f prime, is going to change from a negative slope to a positive slope. And that change from negative to positive slope to a positive slope is going to guarantee we're going to experience a relative minimum at that point. And notice that the increase, decrease are intervals, but relative max and relative min, these are order pairs. These are not, we're not talking about interval here. That's physical. These are physical points, even though the notation looks the same. These are physical points. These are intervals for increase, decrease. Good. Any other questions? So I want you to feel like this is easy, and because every year I see students miss points on these problems, and I want to just hopefully you feel like this is an easy process so that you don't lose points in these, I think, relatively easy problems. Yes, question? Yeah. Okay, let's look at 33. Same process. We're going to find f prime, but now there's going to be that added complexity of dealing with the denominator. Okay, does anybody still need to look at 21? Okay, here is 33. Okay, so first derivative test. Let's get that second term ready for power rule. I'll bring that x up to the top. Make it x to -1. Okay, derivative. 2x becomes, next up, what's next term? -1x to the -2. Okay. Okay, f prime. To help me see this critical points easier, I want to merge it into one fraction so that I can clearly see my numerator and denominator. So I'm going to find a common denominator here. So my common denominator between 1 and x squared will just be x squared. And I'm going to balance each fraction. So here, my old denominator to my new denominator, that's a difference of x squared. So I need to balance by multiplying the numerator by x squared as well. Okay. Second denominator, there's no change between the old and new. So I'll just carry that 1 down. So here's my f prime. Now that I have a nice cleaned up fraction for my derivative, I can set the numerator equal to 0 to find my critical point. Denominator equal to 0. And I'll place everything that I gather here onto my sign line. Now, if I clean up square root of 1/2, rationalize it, it becomes root 2 over 2. You don't have to do it that way, but it helps me remember this around 0.7, so it helps me to pick some easy points for me to gather for my test. Okay, slope sine line. I'm going to place 3 points onto my slope sine line: negative root 2 over 2, 0, and root 2 over 2. But this is around negative 0.7. So I'm going to choose -1. To the left, I'll choose negative 0.5, 0.5. Okay, they're all going to get inserted into the derivative function. So -1, I'll get 2 minus 1 over 1, which is positive. My graph is going to be increasing in that interval. 2 times 1/2 squared, that's going to be 2 times 1/4. That's 1/2 minus 1. That's negative over a positive, which is a negative. I put 1/2 in for x. I'm also going to get 2 times 1/4. That's 1/2 minus 1. That's negative over positive, which is still negative. And then finally, to the right of root 2 over 2, I can choose 1, plug 1 in, positive over positive. Okay, what would you write as your interval increase? And remember, go ahead and cross out those test points, right? You're not going to ever use them again. Okay, what's your interval increase? Okay, and then? Good, okay. Now, what about interval decrease? Good. And then from 0 to 2 over 2. Now, I think that's the safest way to do it. Sometimes you're able to skip over that middle point and then just merge them together. In this case, you can't because there's a vertical asymptote at 0. But rather than deciding whether you can merge them or not, just always separate them. If you always separate them, you're never going to be incorrect rather than having to decide between options. So even if you see 2 intervals that are the same next to each other, try not to merge it because you may get caught with an asymptote where you're going to have to separate them anyway. So if you always separate them, you're not going to run into any issues. Okay, do we have any relative max or relative min? What do you expect at negative root 2 over 2? Relative max, because f prime changes from a positive to a negative. Okay, and then what happens at root 2 over 2? Relative min, because f prime changes from negative to positive. Okay, so practice writing out those statements and focus on your because statements, because that's what allows students to leave out. And then the relative max and relative min, these are not intervals here. These are physical order pairs. So I went ahead and I found these y values by plugging them back into the original function. Yes.
What's the max? What are the min?
The reason why is because you may have a graph that looks like this. because the relative max is only within this region, so it's possible for a relative max to be lower than the relative min. They're not the max. It feels weird to say a relative max being lower than relative min, but that can happen because they're not related to each other. Okay, good. Any questions? Okay, all right, let's move on to today's lesson, which is test for concavity. Page 13. Okay, so now what we're going to do is we're going to go a little further than just talking about slope. We're going to talk a little bit more detail further along than just the slope. But let's just make some observations here. What do you notice about the slopes of these two curves? What's similar? They're both positive, right? But you can obviously tell that the curvature is different, okay? And that's because their slope is changing at different rates. Okay? So what do you notice about the slope here as you move from left to right? Increases, okay? What about here? Decreases, okay? So even though they're both positive slopes, if we dig a little deeper in terms of the rates of change, one is becoming more positive and one is becoming more gradual, one's becoming more negative. Okay. So if you look at, so for instance here, maybe this is a slope of 1/2, right? Then it goes to 1, then 2, then 3, then 4. Right? I'm just throwing out ballpark values here. Meanwhile, over here, maybe you start off with a slope of 3, then 2, then 1, then 1/2. Meanwhile, they're both exhibiting positive slope. They can obviously tell the difference in terms of their movement. Okay, so both these functions are increasing. Yes, that's true. But what do you know about their derivatives? Their derivatives, their slopes, are changing different ways or taking different directions. How's that? So this is leading us into this topic of concavity, which is talking about the curvature of the graph. So I want you guys to draw these two graphs here. So this is what we call a concave up graph. This is where the slope is becoming more positive. Okay, I'll talk a little bit about what that means in a second. Let me fill out this side here. This is called a concave down graph. And this is where the slope is becoming more negative. From left to right. Now, it feels weird to say that it's becoming more positive because you have a collection of negative slope and positive slope, right? But let's just see what happens as we assign maybe some ballpark slopes and look at the pattern here. So starting here at the left side, what do you expect the slope to be around here? Positive or negative? Negative, right? Is it steep or gradual? Pretty steep, right? So let's say we start -4, right? Then it's going to go to -3, then eventually -2, -1. Eventually it's going to hit what? 0, and then it's going to start moving the positive direction. Okay. What do you notice about these numbers here? From left to right, they're moving in the positive direction, right? So if you were to place these numbers on a number line, you're going to continually move to the right, right? You're moving in the positive direction, even though you have a collection of negative and positive values, but the direction is that they're both moving you towards a positive value. So if you ever have a slope moving in the positive direction, it doesn't have to have a full completion from negative to positive. Even if it's just a little bit, this is still considered concave up. Even if there's a little direction, that movement towards a positive sign, like even this is even just that little piece is considered concave up. So if your slope is moving in the positive direction, your graph is going to resemble this. It's going to have this curvature. It's going to feel like a right side up U, right? Or a parabola opening up. Now let's look over here. From left to right, what do you notice about these slopes here? Here I start positive or negative. Positive, so let's say this is slope 5, then 4, then 2, then 1, and eventually 0, -1, -2, -3, -4. If you look at all these slope values are consistently moving in the negative direction. And when that happens, it's going to resemble, the physical graph is going to resemble that of a upside down or a parabola opening down. So all this curvature is coming from, is what we can gather with the second derivative function. Okay, so if the second derivative function is positive, then my f prime is increasing, right? My slope value is increasing, moving the positive direction, and my function is concave up. Okay. If my second derivative function is negative, okay, that means my graph is going to resemble this. My f prime is decreasing, and my function is concave down. And finally, there's something called a point of inflection, POI. This occurs whenever f double prime changes signs. So basically, you can think of it as a transition point from one curvature to the next. So I have a curve here. What does this part resemble? Concave what? Up, okay. But then eventually it's going to transition to a what? Concave down. And then there's that transition point where it's neither concave up nor concave down, and we call that the point of inflection. It allows for a transition from one concavity to the next. It can also go the other direction. I can go from a concave down to a concave up. That's also a point of inflection too. All right, concave down to concave up. So point of inflection, we don't differentiate between, concave up to concave down is a name, and concave down to concave up is a name. As long as it transitions from one to the next, we call that the point of inflection. Okay. So let's look at example 1. Example 1, we're going to gather points of inflection, but we're also going to gather intervals of concave up and concave down. All this is going to come from the second derivative function. So a lot of the process that we did with first derivative test is going to carry over to the second derivative test, or rather the test for concavity, but we're just doing everything from the second derivative perspective. So the first derivative is going to tell us all the information about where the graph is rising, falling, relative max, relative min. The second derivative function is going to tell us about the curvature of the graph. Where's the graph concave up? Where's the graph concave down? And where's their point of inflection? So it's giving us information about the same graph, just a different set of details. Okay, so we're going to first make our way down to the second derivative function because that's where all that information about point of inflection, concavity is going to be stored. Okay, so let's find f prime first so we can move our way down to f double prime. What's f prime going to be? Hmm? 5 thirds times 3x squared. Clean that up. Okay. Okay, we got to keep going, right? If we stop here, then we can find out all the information about slope and increase, decrease. But we want to make our way down to the second derivative. Okay, I'll roll again. What do we get? Negative 40x cubed plus 10x. Now we can stop. Find our critical points, set equal to 0. Okay. Factor, is there GCF we can take out? Next. And then find your critical point. Okay, we have 3 critical points, 0, negative 1/2, and positive 1/2. Okay, create your second derivative sine line. And then choose values in each subinterval. I'll choose negative 1. I'll choose negative 1/4, 1/4, and 1. So guess where I test these points against? Well, the originals will give us ordered pairs, but I want to gather information about the concavity. So they're going to go into the what? Into the second derivative function. We're going to test each interval. We want to know in each interval, is the graph going to exhibit concave up or concave down? So negative 1 then for x, I get negative 10. Negative 4 plus 1, that's negative. So negative times negative is positive. So if it's a positive interval, I want you to put a plus. I also want you to put a u. And that will give you a physical reminder of what's happening there. That graph, this region is going to resemble portions of the u. It may not show the full u, but it will resemble at least portions of a graph that is part of a concave up. Okay, negative 1/4. Okay, back into the second derivative, I get negative times a positive, which will be negative, so negative concave down. Okay, next up, plug in 1/4. I'll get a positive times a positive, which will be positive. If I plug in 1 here, I'll get a positive times negative, which is negative. Now what I can say is I have intervals of concave up, intervals of concave down, and also how many points of inflection do we have? 3, right? Because there's a change in sign here, change in sign is 0, and change in sign at 1/2. And we'll write our statements this way: concave up because f double prime is greater than 0, concave down because f double prime is less than 0, point of inflection because f double prime changes signs. Okay. We still have to do a little bit more with second derivative test. But we will pick this up tomorrow. But there's homework tonight. You guys can try that. I'll check it tomorrow. But tomorrow we can finish this and we can start our review. Okay, we'll review tomorrow, review Monday, quiz on Tuesday. Okay, come up and get your phones.
Yeah, different one.
Okay. Thank you.
It's a big air pocket. I don't know. Technology. Don't even try to do it. It's just. That, Sean's and